Question 4, part 3, to solve this we need to use the sine rule. The reason is, well, just a little bit of thinking here. We've just worked out that this is 9.82, so it looks like we might need that to work out something about this right-hand triangle. And we do have a side angle opposite pair here, but we don't have any other information about that triangle. We don't know this angle, for example, and we don't know this angle. We could work that out, and that is a way of solving this problem, but there's a more efficient way. If we look at the whole triangle instead, then we see that we still have this side angle opposite pair, the 30 degrees and the 8 centimetres. And we know this angle here, so simple sine rule to work out this question mark here. So just try and ignore that line in the middle. So the question mark, I'm going to call it BC, which is what we're trying to find out, divided by sine 65 by sine rule is equal to 8 over sine 30. And if you solve that on the calculator, you get BC is 14.5 centimetres. Question 5. We have to sketch this curve for 3 marks indicating the coordinates of all intercepts with the axes. Okay, well, let's sketch some lines. Let's label our axes. Then we can begin. Right, we have a double root and a double factor, if you like, repeated factor, and a normal factor. So we've got a double root x equals 2, and we have a normal root x equals minus 1. And it's a cubic curve, and it's a positive cubic curve, by which I mean if you were to expand it, you would have a positive x cubed, have 1x cubed. So we're expecting a cubic shape which will probably have this sort of shape, and we know that it has a single root at 2 and a normal crossing the axis root at minus 1. I prefer to sketch the curve first, so just having it turn on the axis. Not my best effort, I might just try that one again. That'll do, as long as it doesn't matter. I'd have got the marks for the other one. For the shape. So normal root at minus 1 and a double root at 2, and it looks like my distance to 2 is the same as my distance to minus 1, but it's a sketch graph, so it doesn't matter. Now remember, before we move on to the next question, we always just have one last read of the problem, and then that's when we notice this word here, all intercepts. So how do we work out this value here? Well, if you were to expand this whole thing, the number at the end would be the y-intercept. But we don't have to expand the whole thing. We can simply just say what's true at this point. What's true at that point is that x equals 0. So if we substitute x equals 0 into the expression, we find that we have minus 2 squared, which is 4, times 1, which is of course 4. Next question. Sketch the curve y equals minus 1 over x squared. Well, if you haven't revised your standard shapes, then you won't be able to do this. You simply will get stuck. If you have revised your standard shapes of curves, then you'll know that y equals positive 1 over x squared looks like this. I'm going to call that f of x equals 1 over x squared. So in part 1, this is, in fact, if this is our definition of f of x, then this is minus f of x, which is a reflection in the horizontal axis. So question 1, you're just looking for something like this. Question 2 might be easier to think of it as y equals minus 1 over x squared plus 3. So I've just changed the order of the two terms there. We can now think of this as minus f of x, or if we redefine this curve over here, then this is just g of x plus 3. In other words, the answer to question 1 translated up 3 units. So another pair of axes. This one over here asymptotes to the horizontal axis, so the new asymptote will be at y equals 3. I'll draw that on. And then your new curve does something like this. Now, just to be super safe, just tell the examiner that you know that value there is 3. You might notice now that we've got 2 intercepts with the axis, we've got 2 roots. So if you were not confident that this might be the answer, you can check by solving y equals 0, or solving for y equals 0 in this equation here. So if you were to rearrange that, you've got 1 over x squared equals 3, or 1 equals 3x squared, which leads us to x equals plus or minus the square root of a third. So there are 2 answers there, and that just, there they are. So that seems to make sense. Okay, I'll rub that out, we don't need it. Part 3, we're told that this curve, which is our answer to part 1, so that curve there, is stretched parallel to the y-axis with scale factor 2. Well, as I tried to do a moment ago, I've still got it there, g of x. Let's let g of x be minus 1 over x squared. And we're told that we're stretching in this direction, vertical direction, scale factor 2. Well, that's 2g of x. So the answer is y equals 2 times minus 1 over x squared. You'd probably get the marks for that, but you'd tidy it up, wouldn't you? You'd write minus 2 over x squared. Question 7. Find the real roots of this equation. Now, those of you who were savvy with your class whiz probably just typed this in and did an equation solve for a power 4 polynomial. Now, don't rely on that in a proper exam. You will not be able to do that, I can guarantee it. We thought we'd got around that with this question, but we've forgotten that the class whiz could solve up to power 4. So here's what you're supposed to do with a question like this. You might ask yourself, how would you have done it if the question was written like that? And if you got the marks in the test, because you use your class whiz on an equation solver for power 4 polynomial, but you don't know how to solve this, then really we shouldn't have given you those marks, because we've told you that you understand these questions when in fact you don't. So how would you solve that? Well, here's what you're supposed to do for this. It is a disguised quadratic. Let y, for example, equal x squared. We therefore have 4y squared plus 3y minus 1 equals 0. And if you, at this point, I'd say that you can use your class whiz, because it is just a quadratic, and that is something that you can rely on it for. Therefore, I think if you simply factorise that, or just solve it and get y equals a quarter, and y equals minus 1, then we just need to solve that as x squared equals a quarter. Just if you remove this, undo the substitution we did, and x squared equals minus 1. We therefore, for this one, have, be careful, plus and minus 1 over 2, plus and minus a half. This one, no real roots. And that's that really, we're done. Just to point out again, to go from here to here, we did use class whiz on an equation solve, but as I said before, if this was 4x to the power 6 plus 3x cubed minus 1 equals 0, you can still do it with a substitution. It's just that you would use the substitution y equals x cubed instead. You'd still probably be able to solve it without any fuss. It's just that you wouldn't be able to type this straight into your class whiz. You have to recognise it as a disguised quadratic. Okay, next question. Number 8. We have to show that this equation can be expressed in this form. Now, one or two people saw this as trying to prove this as an identity, which it is not true. This is simply not true for all x. It's not that we have a triple equals sign here. We have to contort this into this form. Okay, the most obvious thing to do here seems to be to multiply both sides by tan x. But it's actually slightly easier if you first... Do you know, maybe we should do that. I'll show you what I was thinking. If you write that right-hand side as 6 cos x over sin x over cos x, and therefore you can write it as 6 cos squared x over sin x. The whole thing becomes quite a lot easier. But let's do it the way that most people probably would have would tackle it. So we multiply both sides by tan x. Don't forget to do the cos term as well. Equals 6 cos x. Now notice, look at the target. There's nothing but tan. Well, weirdly though, what many of you might actually expand the tans to write sine over cos, but then you're getting rid of the thing that we actually are trying to turn everything else into. So it seems to make sense really to try and keep those tans. Now notice also that we have a 6, and in fact we have a minus 6 on the left, and over here we have a plus 6 cos x on the right. So let's turn that into a 6. Let's divide by cos x everywhere. Well, here we've got sin x tan x over cos x. Here we have just tan x. That's looking promising, isn't it? Minus tan x equals 6. And then you might notice that we have a sine over cos here, so that is in fact just tan squared x minus tan x, and take the 6 to the other side, minus 6 equals 0 as required. Okay, hence solve the equation. Now, that is the same equation. It's always worth just checking it's exactly the same. This is this, but we've just written this in a much better form, which is this one. So really, ignore that. Really, question 2 is saying solve this equation for x in this range. So let's go ahead and do that. So part 2. Again, it's a disguised quadratic, so I might use y again, let y equal tan x, and we have y squared minus y minus 6 equals 0. This time I'm going to factorise it because it's an easy one. Y minus 3, y plus 2 equals 0, so y equals 3, y equals minus 2, so tan x equals 3, tan x equals minus 2, and if we inverse tan those, the left one, we get x equals, I think we get 71.6 degrees. That's a principal value. Now, in tan, to get the next value, just have another little look, we go 0 to 360 here. In tan, to get the next value, you add 180. So 180 plus 71.6, and we have 151.6 degrees. underline all your valid answers. Over here we get x equals, now I'm just grabbing my calculator and checking my working here. Yeah, we get minus 63.4. Now that's not in the range we need, but it's not a problem. Just do 180 plus that to get the first result, 117.6 degrees. That's in, and we can add 180 again to get 297.6. That's in, and we get our 4 answers. Okay, great. Next question. Number 9. Okay, sketches are good. As a general rule, sketch stuff. You've got a circle. You've got centre the origin. Has radius 2√5. And then we have another straight line with equation y equals 2x plus k. And it meets the circle at 2 distinct points. So think carefully, 2x plus k. So roughly speaking, we've got a steepish line. Now, if it was there, it wouldn't intersect the circle at all. So you'd have no intersections. Here we'd have 1 repeated intersection. On this range, we have 2 separate intersections with the circle. Here again, we have 1 repeated intersection with the circle. And over here again, we have no intersections with a circle. So the question is asking essentially what is the range of values of k such that we get those 2 intersections like that. Well, I don't think we have any need for that particular line anymore, so let's get rid of it. Our diagram actually doesn't, unusually a diagram's no longer going to be much help here. What we need to do is solve this algebraically. So think first, circle with centre at the origin, radius 2√5. The equation for that is x squared plus y squared equals 2√5 squared, which is 2 times 2 times √5 times √5, which is 4 times 5, which is 20. Okay, you get marks for that. And it's intersecting this here. Well, whenever you're dealing with intersections between algebraically defined mathematical objects, simultaneous equations is the way to go. So we know that y is 2x plus k, so I'm going to write y as 2x plus k. Now have confidence here, because we're looking at an equation now that has 2 variables in, x and k, or technically k is a parameter and x is a variable, but 2 unknowns. How are we going to solve for k if we have 1 equation and 2 unknowns? But let's worry about that in a minute. We know we've done everything right so far, and surely we need to expand this and see what we can make out of it. So let's just do that and then, take stock in a minute. Again, use my little tip of coming out the way and just doing any expansions out the way where they're not going to interfere with your main river of working. I'm going to combine those two into a single term, so let's come back over into the main river now. We've got 4x squared plus 4xk, that's my 2 combined terms, plus k squared equals 20. Now, you might want to write that as 5x squared, just combine those first 2 terms, plus 4xk, and since it looks like a quadratic expression, set it equal to 0. Right, again, you've got 3, I think, marks out of 5 at this point. Now we need to find the values of k for which the straight line meets the circle at two distinct points. Now this is quadratic in x. We've got 5x squared, we've got 4k lots of x. And we have this constant here. Let's just tidy that up a little bit. In fact, I'm going to write, instead of xk here, I'm going to write that as k. 4k times x. So we have a quadratic equation in x, and we want it to have two distinct solutions. And this is where you need to invoke the discriminant. b squared minus 4ac, and to get two distinct solutions, we need that to be positive. So set that up as an inequality. Then we can substitute into it. b is 4k. A is 5. C is that bracket there. And greater than 0. Great. Multiply things out. Be very careful. 4k all squared is 16k squared. And then we've got minus 20 lots of k squared minus 20. Multiplying out further. Minus 20k squared plus 400. And simplifying, we have minus 4k squared plus 400. We could divide by 4, but I'm first going to take my negative k squared term to the other side of the equation. Be careful dividing by a negative, because if you divide by a negative with an inequality, you'd have to change the direction of the inequality, which we could do, but I prefer to do this because it's much more obvious what I've done. I don't then have to remember this extra rule about changing the sign of the inequality or direction of the inequality. Now I can divide by 4. K squared is less than 100. For a square number to be less than 100, that number must be trapped between minus 10 and 10.